Good morning. Last week we didn't have a lecture because I couldn't come. Things were annoying, so I had like 1 hour later to the lecture. We will be the lecture today, and unfortunately we will miss the last lecture, which will be about the level sensors. So today we'll discuss the speed sensors and then acceleration sensors. You will see that the speed sensors are very similar to position sensors. You will also see that many principles used for speed detection are similar to detecting position. So we will see some old stuff from last weeks. We will start with some simple electromechanical sensors. So here is just a list of types we will discuss. So we will discuss electromagnetic sensors. We will discuss optoelectric sensors, which will be quite similar to incremental motors. And then we will discuss magnetic sensors. Obviously, the possibilities how we can measure speeds are much wider. So again, this is only just a selection. And we will start with some electromagnetic principle. The sensor is called the tacho generator. The tacho generator is a machine that is quite similar to an electric motor. So to take a look at that generator, you will see what is happening inside. Inside there is a coil. The coil is connected to the motor and is rotating with the shaft. So this shaft is then connected to the shaft that will measure speed. This coil rotates in a magnetic field that is created by a permanent magnet that is on the stator side. So here in the center of the permanent magnet. And those poles are made from iron, and they are used to conduct the magnetic flux. If you look at the cross-cut through the device, you will see that this green part is the coil. So this rotates with the shaft. The coil sections are connected to a commutator. That's this silver part. And this commutator is divided into several sections. So every coil is connected to its own individual section of the commutator. The permanent magnet here creates the magnetic flux. The magnetic flux goes from the permanent magnet through the coil into the outer core and back to the permanent magnet. And as this coil rotates, we will have induced voltage in the coil. So the induced voltage in the coil is an AC voltage. So we need to rectify it. For this reason, the commutator has multiple sections, which you see here, and the brushes here connect only 2 sections at a time of the commutator. So the commutator acts in fact as a mechanical rectifier. So on the output of the DC tacho generator, we will have voltage, and this voltage will be proportional to the speed of the coil. So that's what we want to measure. It will be proportional to the strength of the magnetic field. So the stronger the magnetic field, the higher the voltage. Nevertheless, this will be a constant value. So it will be just some number relative speed to voltage. And the third value influencing the output voltage is the construction. So how is this flow down? What is the size of the area? But during the operation, this will not change, so it will be a constant as well. Why is it similar to a DC motor? Here you see a rotor of a DC machine, and it has exactly the same construction. So here we have a coil. Here we have the coil sections connected to the commutator, and here there will be brushes connecting the commutator to the state. So the construction of the group is exactly the same. The only case of DC motor is made from copper. Here it is covered with a silver layer because we want very good conductivity from the commutator sections into the brushes. The DC motor has brushes from carbon. The Teco generator has brushes from silver layers. So again, it's in order to reduce the losses of the commutator and to measure the voltage precisely. As I told you, the output voltage of the DC Teco generator is proportional to speed. So here we have the equation. The output voltage is proportional to angular speed, omega, and this magnetic flux phi is the strength of the magnetic field, and this constant CDC is describing the construction of the machine. So the size of the area, the dimensions of the poles, and so on. So those two values will be a constant value, and we will see that the output voltage is a linear dependence of the speed. So that's quite good property. We have linear dependence. However, the output voltage will be measured with some device. So it will be measured with a voltmeter. And if I measure something, I wrote the output of the source. So it means that I need to choose a voltmeter which has quite high input resistance, because the current that I take from the Teco generator should be low. In other words, the ideal load for a DC Teco generator should be infinite, or should be some quite high input resistance. I will later show you some examples of Teco generator data sheets, and there you will see the current is limited to max 10 milliamperes, 20 milliamperes, some milliamperes. So when you load the output, you will change this linear characteristic into something else. The output will still remain linear. So let's say here is angular speed, here is the output voltage, and if I have an unloaded output, I will have a linear dependence. So this equals R0 going to infinity. If I load this circuit, so we can imagine it's source plus some load, it will still be a linear dependence, but there will be a voltage drop on the brushes, for example. So the loaded characteristic will look like that. It will be linear, but it will give you a lower voltage. So let's say, this is a low value of the load resistor. So just looking on the steady state characteristic, you are not able to tell that I have changed my steady state characteristic by the load. So that's the reason why it is important to know what is the load resistor. In other words, what is the input resistance of the load meter. Because if you don't know that, then you may not have a defined dependence between the output voltage and the speed. Typically, the constant describing this part of the equation gives you the relation between speed and voltage. So for example, the Teco generator you have over there has 80 volts for 1000 RPM. One we used in class was the same. We had another small Teco generator which had 2 volts for 1000 RPM. So we will need to look in the data sheet or on the device for the relation between speed and between the output voltage. There is another issue with the commutator. If you look on the sections, we see that we have a limited number of the sections. So the commutator acts as a rectifier. If we want to have an ideal rectification, it would in theory require an infinite number of the sections, an infinite number of the blocks. The reason is the output voltage. If you look at this picture, here those peaks are the voltages that you would measure on individual coils on the road. So each coil will produce you an AC voltage. If every coil is the same, will have the same amplitude, but it will be phase shifted because the sections of the coils are shifted on the rotor as well. What is the commutator doing? It is in fact just taking the peaks of the coils because it connects the coil to the output only when the voltage has its maximum value. And you see that I stated this peak and this peak and this peak and this peak and so on. There are many sections. And as the number of the sections is limited, we will always have some remainder delta V after the rectification. So the rectification is never perfect, and this value delta V will limit us the precision with which we can measure the speed with the DC generator. You can imagine that this is some value. For example, that this generator has 80 volts or 1000 RPM, and this value of delta V is about 1% of the value of the output voltage. So typically with a DC generator, you cannot measure precisely than for about 1% of the range. If you want to measure precisely, you need to use some other types of sensors. For many applications, the DC generator is a sufficient sensor because we typically do not require such high precision, let's say only 1% or something like this. Well, basically here you see the same image I brought here. So we have the output voltage and dependent speed. The unloaded output is a linear dependence. The loaded output is a linear dependence as well. But we see that there is a difference in voltage between the loaded and unloaded output. So for this kind of output, it's not valid only for DC generator, but for any kind of sensor that has a voltage output. If you load it, you lower the voltage and it can influence the reading. So you need to be careful about what instrument you choose for which kind of sensor.
So the unloaded output corresponds to the infinite resistance.
Yes.
If it has infinite resistance, why you call it unloaded? It has load. It has infinite load.
Well, infinite load means like it's disconnected. It's like you take a very low current from the source. So that's what I mean here by unloaded output. And by loaded output, I mean that you connect a voltmeter with 10 kilo ohms resistance. Okay. So here are some examples of generators. You see two versions. One version with a shaft. So here you need to connect the coupling between the generator and the machine. In this case, we see that it's hollow without a shaft, so we can mount this directly to the shaft of your machine. So this is the commutator here in this coils. This is the stator, and there are brushes. There has to be brushes, and we will have the voltage. Now let's take a look on some specifications of the generators. So what can we expect? The typical speed is around, let's say, 4,000 or 5,000 RPM. Sometimes it can be 10,000 or 2,000 RPM. So we are in, let's say, lower speed range, but for most applications this is quite sufficient. The output voltage is typically several volts or several hundred volts for 1,000 RPM. So for example, this one gives us 50 volts for 1,000 RPM. This one gives us 200 volts for 4,000 RPM. So it's about the same value. What is important here is the maximum output current. You see here it's 10 milliamperes, 17 milliamperes, 50 milliamperes. So it's quite low. So a DC generator is not a generator that you can use to power a pump or a heating. So it's a device used to connect just a voltmeter. If you look on the value of current square. Will 0.5 or 0.5 increases. So it means what is the difference between the linear dependence and between the real dependence? So it's quite for easy to generate. And the remaining parameters are also just only for some relations. Any questions? Okay, so let's switch to something else, which would be an optoelectric sensor. We saw a very similar image when we discussed position sensors. True? So where can we see a similar image? Or how could this work as a speed sensor now? So this is a similar image when I know proximity sensors, but incremental encoder. The incremental encoder uses exactly the same principle. We have a light source. It's about here, but it can be a light emitting gun, for example. We have a light detector, and we detect if the light is passing or not through some slots, through some holes, through some marks. So in the case of an incremental encoder, this was a glass disc with some marks or black fields, white fields. And in this case, a typical speed sensor uses holes or uses some beads and some slots. So we measure if I see the light passing through the wall or if it is blocked by some piece of material. So it means that on the output of the detector, we will see a rectangular pulse. And how do I change this to speed? How do I look on this signal and say, okay, the speed is 500 ampere? High voltage? No. So something easier.
This the pitch will be low or high.
Yes, that's true. It can be. Yeah, so I can either measure the time between the pulses, or I could know, okay, I have 8 marks per one revolution, so I can measure how long does it take until I measure 8 marks, for example. Or inverse, I can measure the frequency of these pulses, which is exactly what we want. So it's quite easy to employ this kind of sensor. There is one disadvantage. This particular sensor is good for clean environments. So typically it's not automotive industry or some machines, for example. It's environments where you expect that there will be no dust, no particles between the light source and between the light. There is one example where exactly this kind of sensor is used. You see this, where, well, maybe not, maybe you saw this, where? So this is from mouse, but it's from a mouse with a ball. I don't know if they are still used today. It's not so old. So how does this work? If I run that, this pair, this black rectangle and transparent rectangle. The transparent rectangle is a light emitting diode, and the black rectangle is the transistor. And here you see I have some small wheels here, and here, both axes, and the wheels have slots. So when this is assembled together, when I move the mouse, the ball moves. There are shafts here, and it moves the wheels, and it's working exactly on the same principle. It detects the passage of the light. So when you turn on the PC, the cursor of the mouse starts in the middle. So maybe for everyone here is the image. So that's the ball from the mouse. This is the wheel. You can see slots. And here you can see this is the photo detector. This is the photo dial. And here for the detector is the same pair. Here this is just some transmission from the wall to the wheel. So if I move the mouse, it moves with the wall and it moves this wheel. Similar ways for the wheel. If you sure if it's really visible, this part is similar wheel like here and similar pair of photo detectors that detect I'm moving the wheel. There are, so typically it can look like two components like you see in the mouse, or you can buy such part that has a pair in one component, so one is item in dial, second is photoresistor. So this works either looking the light or moving the light. The second possibility, you have some reflective object or some reflective mark you can do in a shaft, for example, some sticker that you will place on the mark on the shaft. You can have such a component which is light emitting diode plus the photo detector, and I detect reflection. So if the reflective mark is there, I see the reflection. If it's not there, I don't see the reflection. I have some examples here of that all are reflective types. So this is the reflective type, and this is reflective type as well, and this is photodiode, that is just the detector. So the source. Light source is a standard light emitting diode. Well, typically, this is just a typical component of how you can buy it for less than $2. Some questions? Okay, so let's try something else. When we discuss position and proximity sensors, we discuss also inductive sensors. So I told you that inductive sensors are quite good for the industry because they are quite robust, quite reliable. They provide us voltage, like I said, position. And now we will use this to detect speed. Here I have some examples of inductive sensors. So all this that I will send you now are several kinds of inductive sensors, and we will also discuss what's inside and how it's important. So inductive sensors, as the name implies, we will measure the changes of inductivity. Typical use of this principle in speed sensors is not to measure the changes of conductivity, but it is to measure induced voltage. So we prefer to measure voltage because voltmeters are much similar than inductivity meters. So the typical arrangement of an inductive sensor for speed is the following. We have a coil, that's this red part, and we need the source of magnetic flux. So typically, the inductive sensor has a permanent magnet inside. It doesn't need to be very strong. It can be like a rod of iron that is magnetized. The important thing is that it creates a magnetic field around the sensor. We know that the induced voltage typically depends on inductivity and depends on changes of magnetic flux over time. So different when the sensor looks at the deed or when it looks at the land. So this is what changing the delta of the magnetic flux. So the important thing for the inductive sensor is that this wheel with marks needs to be from a ferromagnetic material, iron, for example.
This flux is
Yes.
so it passes through air or magnetic.
The cross section is the same, but the material is different. Let's try this. Okay, this is my permanent magnet, C, D, yes, and the magnetic flux goes from the sensor to the area, to the D, and again here. So here I have air, here I have iron, here I have air. When I look from the sensor, looks and the marks, let's say D is over here, it looks air, 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 air. And when the mark moves in, it will change the value of the magnetic flux because the material keeps changing. And then some animation will maybe show you a little bit more. So this is a simulation of this kind of magnetic sensor. This is the permanent magnet that produces magnetic flux. The magnetic flux lines are the lines that you see here. This is the wheel with beads, and the color from blue to red is the strength of the magnetic field, or yes, strength of the magnetic field. This wheel will move down, and we will see that the flux lines will change their positions, and this will cause us the change in the magnetic flux. So let's take a look on here you see the wheel is moving and the magnetic flux is changing. So this is the simulation with finite elements. You can see the voltage. If you make the correct choice between the size of the sensor and the size of the size of the feed, you will see that the voltage is sinusoidal voltage. So typically you will see such an output on the sensor. This is the magnetic part, it's a sinusoidal voltage. It doesn't really change very much, but you can still detect the changes. This is the change in the flux, which will be some sinusoidal input times some times will give us some sinusoidal voltage. So if I have a voltage like that, how can I detect the speed with this? Again, by measuring the frequency of the voltage. So it's quite easy to use this kind of sensor. It's also quite precise. It's much more precise than the DC generator, for example. You can measure changes of speed, let's say 1%. This kind of sensor. There are typical applications. Typical applications are to measure speed of some gear wheels, for example, or in the automotive industry. I would say that it's less common than to measure some gear wheels. Here you see such an example. This is a gear wheel. This is the inductive sensor. I detect the passage of beads, and I measure the frequency. The distance between the sensor, the wheel needs to be quite small. We need to actually typically it's around 1 millimeter. So this needs to be quite small. Again, some sensors are able to measure up to 5, 10 millimeters. This is the example of a sensor. You can tell from the outside, just by looking at by making simple experiment, this is 10 millimeter sensor. You can take some piece of ferromantic material, like a screwdriver for example, and when it is attracted in the middle of the sensor, means that there is a permanent magnet, and probably it is a millimeter sensor. It could also be a whole sensor for yes, frequency of the, let's say, how fast are the things passing under the sensor. You can see here something more advanced. There are teeth missing. Why do you think there are teeth missing? Yes, some kind of mechanical problem, or is there a reason why there are teeth missing? It could be used for ABS, however, in ABS, more difficult is to use the next sensor to be discussed. In theory, yes, it could be used. Why? I don't have the teeth here. Sorry? Someone broke that? There is a reason why I don't have teeth. If, let's say, I open this section, I have regular teeth. So what would be the output signal? The signal is sinusoidal voltage. So I can use this to detect position. But in some applications, I want also to detect the position of the wheel. So I need some reference mark. I need some place where I know I'm now at this position. So let's assume that there is only a single direction of rotation, that the shaft can rotate only in this direction. So if I start here, C, D, C, D, and so on, so I will see a sinusoidal voltage. But when I don't see the teeth, there won't be any voltage. So there will be a straight line there. Then teeth start again, and there will be again sinusoidal voltage. And I know, okay, here I missed something, and this will be my reference mark. I know that this is in position without teeth. It's not very precise, but for my applications it's quite sufficient. Typically you have so many teeth, 50 teeth for example, 100 teeth on the wheel, so you can easily detect the position without teeth. Of course, this is working only if it's rotating only in one direction. You cannot tell it's rotating in the opposite direction. You could tell if you apply two sensors that use the same principle like the incremental or have two signals exchange. That could be. So the typical applications for automotive industry or machinery with speed of some tools. What else can we expect? This is an active sensor from the automotive industry. For this kind of sensor, you need to be aware that the signal that we measure from the output is quite sensitive to the size of the area. The smaller the area, the higher the induced voltage, the bigger the area, the lower the induced voltage. For frequency, if you measure frequency, it's not a problem typically, but if your voltage is below a certain level, you won't be able to measure frequency. The second important property is that this kind of sensor can measure only non-zero speeds. Because if you look on the equation relating induced voltage and magnetic flux, you will see that induced voltage depends on the change this kind of sensor, as we see in the picture here, it's about 15 kilowatts. So it seems high, but you need to count that one pulse from the sensor will be coming from one arm or one beam on the wing. So you take this frequency, divide that by the number of arms that you have on the wing, and you will get the speed of the wing that is out. The size of the area, you see, it's quite small, 0.8 millimeters, plus minus 0.3 millimeters. So we need to precisely adjust the distance between the sensor and the wing. What happens if you don't do this? We can see this on that picture. There are 4 curves, and they are plotted for 2 different items. Here, this line, and this line is for distance 0.5 millimeters. And the other two, this one and this one, is for distance 1 millimeter. So the bigger the area, the lower the input voltage. You see that this line with the squares has 0.5 millimeters, so it's quite close to the wheel. And this kilo ohms, it's the low resistor. So it's, let's say you can imagine that it's a input resistor of low meter, very much. So 100 kilo ohms, not really high level. So in this case, you see that the dependence between speed and output voltage is almost linear. Only at this end, higher speeds, we have some small differences. When I use the same sensor with the same area, 0.5 millimeters, I load it with 10 kilo ohms. You can see I'm limited by range from 0 to 4,000 RPM, let's say, or 5,000. Because here I have a linear load, I have a constant value. So here I can tell, okay, it's 5,000, or it's 7,000, or it's 8,000. So just by taking a voltmeter with lower input resistance, you will again limit your range. The 2 remaining curves are for the same sensor, but mounted only in the distance of 1 millimeter. So this line is the output of the sensor when loaded with 100 kilo ohms. So we can say, okay, we have lower voltage than 4.5 millimeters, but we have still very many values from 0 to the maximum speed. But if I load it, I will limit the range from 0 to maybe 4,000, maybe 3,000. So again, just by loading that, I will increase the range. So we see that it's quite important to maintain the specified area and to maintain the specified load of the sensor. Okay, that's all for the sensors. And the next sensor will be a magnetic sensor. It's also called a Hall sensor because it detects the changes of the strength of magnetic fields. How does it work? We need a Hall sensor. A Hall sensor is a semiconductor component that measures the strength of magnetic fields, and the output is voltage proportional to strength. It looks like this. It's like a small rectangle and measures the output voltage. So now we need some source of magnetic fields. For this kind of sensor, there are 2 possibilities. You can either have an active sensor where this part is a permanent magnet and it is producing magnetic fields. So this is a sensor, and I measure if I see the North Pole or if I see the South Pole, and eventually how it's moving. Those sensors are typically available like rings that are pre-magnetized or tapes that are pre-magnetized. So you can just put this ring or this tape on your object, play the sensor, and can work with. then this tape, it's really a tape. It's made from material that can change its magnetic orientation, and this whole sensor is the leader that it's using to understand. Let's definitely use also to sense position. How does it look like? Well, from the outside, it looks exactly the same like in the inductive sensor. So those are automotive applications, automotive sensors, those are industrial sensors. You saw one of the sensors in class in one cycle where we discussed position sensors because it's also using the best position sensor. What properties does it have? Well, those are automotive specifications. It's again limited in maximum frequency, so you take the maximum frequency divided by the number of marks of the application, and this will give you the maximum speed. On the other hand, the magnetic sensor is not limited in minimum speed. It can detect even if this wheel is standing still. So it can still detect that there is an object under the sensor. So it means that the whole sensor can typically work from speed 0. You can see that here. This kind of sensor works from 0 Hz to 15 kilowatts, or smaller version of that works from 2 kilowatts from 2 Hz to 1 Hz. So either 0 or very low frequencies. The size of the air gap has a similar value like for the inductive sensor. So again, it's a smaller gap, typically around 1 millimeter. If you look at the machine, it says okay, from 0 to 5 to 1.4 millimeters. So smaller gap to be precise. Why is the name of the main line same reason as for inductive sensor? Well, if the air gap is too small, the sensor could hit the wheel. So it's purely for mechanical reasons. Usually, the smaller the air gap, the better, but we need to also consider the precision of the rotor, also vibrations that cause the sensor hits the wheel. So typically, this is let's say normal value that you can still it's a typically normal values. You can see the range for temperatures that's similar to the inductive sensors. This is let's say standard range for automotive applications from around -4 to 7 centimeters to work in this temperature range. The output typically is just say yes or no signal, ones or zeros. Sometimes it's a non-conductor circuit, which means that you need to connect an external resistor so those speed sensors, magnetic control sensors, they have a digital output. So digital output is they don't measure the distance between the sensor and the wheel. They just measure if the mark is there or the mark is not there.
How can you differentiate between both magnetic and the inductive sensor?
From the outside, you need to do the time and the data sheet. Because here it has the same composition like the inductive sensor. It's a permanent magnet and typically Yes. I forgot to tell you that this wheel also needs to be from some permanent material. So the typical application of this kind of sensor is in the automotive industry and the ABS system. The sensor is mounted on the wheel. There is some ring of leads. Looks similar to this wheel. this sensor is that it is quite robust. It doesn't require any maintenance, and it can work also with dust, with dirt, and so on, ice. So if say this is the video, I don't care because some dust that will be the sensor. It will measure just the injection, which is the temperature. So that's the typical application of sensors.
What is the purpose of this?
The screws,
Yeah.
just to set the distance between the sensor and the agent.
The object will be here, and the sensor is here.
Yes.
What is the purpose?
You mean sensor or this one? Let's say this is the sensor. This is the nut. This is the nut. Here I will have the jack and I will have a holder somewhere here. Some screws. So if I screw this in this place, then the holder screw that in place, I can set the distance. If I move it down from here to there, like this, I can move the sensor and I can change the distance with the sensor and the engine. So this now is just to tighten the Any other questions? Okay, so we'll finish with optical sensors. We'll discuss stroboscope. I will just for this time switch to check presentation because I have a nice animation there. So the image is the same, but I will explain the animation also. We're going to switch to the animation. Okay, so the stroboscope. One group so that for your that aspect. What is inside the stroboscope? There is a source of light, source of flashes. That's this bulb. Typically, it's a fluorescent bulb because it can easily work with flashes. And this source of light shines on some rotor. So when it shines, this will be yellow. This is the rotor, the shaft of the machine where when you speed. And you need to place a reflective mark on the rotor. The reflective mark can be a sticker, can be some paint, for example. And the assumption is that when this light shines, I see the mark. When the light doesn't shine, I won't see the mark. The shaft is rotating. We'll start in the upper position. Now, I saw the mark in the upper position. I can change the frequency of the flashes. So if let's wait until now. The mark is moving, I will see because the light is not shining. And the second flash was before the mark could reach its original position. It means that the frequency of the flashes is higher than the speed of rotation. So this is wrong. I see the mark moving against the movement of the shaft. The second option is that the frequency of the flashes is lower than the speed of rotation. So I start in the upper position again. Let's wait again. Once more. This. Now, top position, I So the mark will pass through the original position, and I will see it here, I will see it here, I will see it here. So in this case, the mark is moving in the same direction like the shaft is rotating. And the correct settings is to set the frequency so that I see the mark always in one position. So it works that I am changing with the knob of the stroboscope the frequency of the flashes until I see the mark standing still at one position. So this is the correct setting. Several problems with that. What if the frequency of the flashes is doubled compared to the speed of rotation? I see the mark in one position, then I see a second mark in the other position, and then I see again the first one. So when the frequency is doubled, even if you have only one mark on the rotor, you see two. But you can easily distinguish them. Similar is when you have triple frequency. So my frequency of the flashes is 3 times greater than the speed of rotation. I see 3 marks. I see one here, second here, and third here. So this is quite good. I can distinguish it. But what happens if I have frequency equal to 1/2 of the frequency of rotation? I see one mark, which is here. Then the mark passes the entire revolution, and I will see it. And only when it passes the second revolution, I see it. So it passes that 2 times, or 3 times, or 5 times. So the correct procedure how to work with a stroboscope is to always start from the highest frequency. Because if you start from the highest frequency, it means that you will see 2 marks, 3 marks, 4 marks. But you will be sure that if I see 2, it's correct. I can identify the frequency that is shown in this stroboscope 2, or I can continue to decrease it until I see only 1. So never start with a stroboscope from the lowest frequency, because then there can be any number of marks passing and you will not see it. Questions? Okay, great. So let's finish with accelerometers. Accelerometer is quite related to speed, because acceleration is a change in speed. So we could, in theory, take some signal of position sensor, speed sensor, and we could calculate the derivative and the different acceleration. For many applications, we want directly the output of acceleration sensor. The sensors for acceleration, they typically do not measure directly the acceleration, but they measure some effect of the acceleration. And typically, this is inertial force. For Newton's law, we know that inertial force equals mass times acceleration. There is a minus sign because the inertial force acts against the movement and cause the force. There are many principles for accelerometers. We will discuss just one, which would be capacitive sensor. So we see that either we can transfer acceleration to changes in displacement, so basically position sensor again, or we could measure the force caused by some movement or some object movements. Why we have so many principles? The reason is that in different frequency ranges, we have to use different principles. So not all sensors will work for all frequencies. Some will be good for low frequencies, some will be good for higher frequencies only. You can see the comparison frequencies in this table. Here we have frequency in hertz, so from 0.1 to 100,000 hertz. And basically just discuss the capacitive sensors because that's the sensor you have and you use that maybe every day. So we'll just discuss capacitive sensing. The principle of a capacitive accelerometer is really easy. We have a beam, and on the end of the beam we have a mass. Fine, and this beam is fixed on one end, some hole. There are two electrodes. One electrode is on the movable part, and the second electrode is on the fixed part. If I now try to move the sensor up, the inertial force will try to move the mass down, and it will decrease the distance between those electrodes. So I can measure capacity between those two electrodes. So if I do what's what? Yes. This beam is flexible, and the mass is potentially moving. So if I move maybe let's go ahead. This is the mass, and this is the beam. I move this. So if there is an acceleration upwards, there will be a force pulling the mass down. So it will change the capacity between the electrodes. This could be used directly to measure the changes in capacity. But today we know that this kind of sensor will have a nonlinear statistic characteristic. How it will look like? Well, yeah. Let's say this is the distance B, and this is the capacity C. So if I move this up, D will be smaller, and the statistic characteristic will look like that. So that linear dependence. We prefer linear dependence, so we can make this a differential sensor. It means that there will be in fact one electrode on the mass here, the second electrode on the mass here, and there will be a third electrode up that part. And we will measure changes in capacity between the electrodes. Skeletal diagram, this is from the sheet, looks like that. This is the movable part. This is the electrode with the mass attached. This is the fixed electrode. This is the fixed electrode as well. If I move it to the right, I will increase this distance and decrease that distance. If I move it to the left, I will increase this distance and decrease that distance. So I will be measuring the changes in capacity of two capacitors and can connect them to a bridge, differential bridge, and I can develop the output voltage. In reality, it looks like this. This is a chip that you can buy. It's not so expensive. It's an accelerometer. It looks like this. In this box there are accelerometers. This one. And if you look under the microscope, you will see similar structures. So this is the set of electrodes. This is the electrode that is below. You see this is the center mass, this cooling. And this set of electrodes detects movement in this direction. This set of electrodes detects movement in that direction. So in fact this is a 2D accelerometer, it detects in X and Y axis acceleration. And this electrode is fixed, this electrode is fixed as well. And together they form a differential capacitor. And if I move the mass down, I will detect changes in capacity here and changes in capacity here. A similar structure is shown here. One set of electrodes. This is moving with the mass that is in the center. This is the second set of electrodes. So if I move it up, I will move those electrodes up. This distance will be smaller. This distance will be bigger, and I will change the capacity. Now, Typically, accelerometers that you can buy today have a range between 2 and maybe 16, 32 Gs. Depends on the application, but typically you need more than 16. Typical output is either digital or analog. Some of those accelerometers have analog outputs, either the output is a voltage proportional to acceleration, or you have a digital output typically with an I2C, or speed bus, some digital buses. I2C is 2 wire experience, 3 wire bus. The digital output, this is for analog accelerometers, is given in millivolts per G. So how many millivolts you measure to acceleration? Well, in the video we see 3D accelerometer, 3D accelerometer. So some of them go today. We have 3 outputs, like 3 analog outputs for 1 digital outputs. Well, typically the power voltage, the voltage power is maybe 3 volts, 5 volts, something like that. And the offset here in this table says that the voltage for 0 acceleration in that particular axis is 1.4 volts. The reason is that we have 2.8 volts per voltage. In the middle, we have 0, 1.4 volts, and if the voltage goes in one direction, we have this sensitivity, we have positive acceleration, if it goes in the other direction, we have negative acceleration. It means the flow is like that. Okay, that's accelerometers. And we'll finish with gyroscopes. What is the difference between a gyroscope and an accelerator? Yes, gyroscopes are just angular changes in angular velocity. Accelerator just changes of linear velocity. Yes. Is that asking something?
No.
Okay. Fine. So we will see that it works in a quite similar way to the accelerometer. It can measure changes of capacity and translate them to changes of angular velocity. The most common principle in gyroscopes that we apply today is to use Coriolis force. What is a Coriolis force? As it written there, I'm just asking. What? Okay, let's say we have an object that is rotating. This object is moving at the same time, and then we will measure some Coriolis force. So this is exactly what happens in a gyroscope. We have a rotating object with some angular velocity omega. We have some linear displacement V, and there will be Coriolis force given by this direction. So the amount of Coriolis force depends on the speed, the linear speed, and the rotational speed. It would be hard to make an object rotate in a capacitive sensor. So the gyroscopes, they do not rotate with the rotational speed omega, they vibrate with some speed. So then this is what happens inside the gyroscope. We have a mass. This mass is vibrating in this direction, left and right. And as we apply some angular speed, we will measure Coriolis force in this direction and for this mass in the other direction. So again, we will change that into capacitive sensing. So let's imagine this structure. It is a set of electrodes. So here there is a set of electrodes, here there is a set of electrodes as well. I will measure angular speed along this axis, and I will make this structure vibrate. If there is an angular speed around this axis, the coils, of course, for this set, that will be moving in this direction. For this part, it will move in that direction. So on one side, I will have the electrodes closer, and on the other side, I will have the electrodes farther away. This is what happens here. Here you see I can have two sets of electrodes, one electrode here, one electrode there, and one electrode here. If it rotates, this electrode is closer than this electrode to the source. So on this inside, the structure looks similar to an accelerometer. The distinction is better, but I just want to say here the scale, 500 millimeters, so quite small device. We have the same technology that we saw in the video. The structure is better visible here. So here we have the detector of the coil's force, which is in fact this set of electrodes here, so coils in one direction, here. So it detects the direction of movement, and the direction of rotation in this case is so here. So if I try to rotate that with some acceleration, so then with acceleration, here I have a different distance than in this space. Details, so here you can see again same sets of electrodes like in the case of an accelerometer. Now we know that it needs to vibrate, so we need to produce some vibrations. It's all down in the chip. I just want to show you here the internal structure of the chip. This is a 2D accelerometer, so two axial directions. Here you can see again the differential capacitor that goes to the electrodes. We amplify that, and we want to suppress the vibrations that we use to measure the force. So that's basically this part. This is live and nice to the vibrating mode. This then subtracts the vibrations from the output signal, and on the output we will have some signal proportional to the acceleration in one axis or the axis. Those channels, this channel and this channel is the same. It's a 2D gyroscope. You can measure the axis. Typically, the gyroscopes have problems with changes to temperature. So we have to offset the temperature changes. Some of them are compensated, some of them are not. So it depends on the application. It can be expected. Well, the sensitivity of the accelerometer of the gyroscope is given in some units per degrees. So in this case, it's an analog gyroscope, so output is voltage, so millivolts. dPS means degrees per second. So I will have 0.67 millivolts for 1 degree per second. The maximum range is about 1,500 degrees per second, depends on sensitivity, about 360 degrees in revolution. So it will give you an idea how fast those accelerators are. So when you take the accelerometer and gyroscope together, you can create something that's called inertial measurement unit. Here you see two examples. The one on the right is a cheap one, which you can use for model airplanes, for example. The second one is an industrial version used for airplanes. They use the same principle and different robustness and for detection. Both are equipped with 3 accelerometer. So that's one of the chips, I don't know which one. 3 accelerometer that measures the orientation. Magnetometer, we discussed that it's used like an electron compass to detect where it's stored. And typically for airplanes you need to measure the altitude and pressure, so there is a pressure sensor this chip measuring the pressure of the air. It can also give you altitude of the temperature. Typically almost all comparison between those two units, what ranges, so the accelerometer